thank you so much for turning out to hear the best of both worlds. Java persistence with NoSQL and SQL. Now, how many of you program in Java a lot? Okay, we got the right crowd here. Okay, we were thinking of a subtitle for this talk, and we came up with hardly strictly SQL, and they didn't like that so much. So we thought, okay, about hardly strictly Java, and they said that's really not going to fly in this conference here. So you're going to hear a bit about Java and a bit about not Java. And you'll hear a little bit about SQL and a lot about NoSQL. We're going to tag team this presentation. We've never done this before. So I was going to do it all by myself, and then JD wanted to do it all by himself, and then we just decided we'd split the baby right down the middle. So as a way of introduction, I've been programming in Java for, 20 years? More than 10, less than 20. I was involved in the Java EE development for the SQL program, the Java persistence, and Java data objects. Anybody here know about Java data objects? Okay, so that was one of my pet projects for a while until they decided that they didn't need to do Java data objects as a thing anymore. And I've been involved in the MySQL team and the MySQL Cluster team since Sun acquired MySQL, and then Oracle acquired Sun, and then it all became one big happy family. So that's me. I've got a bias, not against SQL, not against Java, but I think the world is big enough for a lot of different solutions. So that's me, and here's JD.
Thank you, Craig. And I'm JD, John David Duncan. I joined MySQL AB, a little startup, in about 2004, and have been on the ride ever since. So we're going to talk a lot about MySQL Cluster. We're going to talk about many different languages and programming environments. But MySQL Cluster is really the common theme, except a little bit of what we talk about will also apply to traditional MySQL and NODB. So when we get to the Node.JS stuff through JavaScript, that has multiple backends, and a normal MySQL client is one of them. But the basis of, in fact, if we go to our best of both worlds title, that comes out of MySQL Cluster and its kind of unique position, we think, of being a low-level database, a low-level data store that's capable of really high performance, and also happens to have good connectivity with the world's most popular open source SQL database. So the standard Oracle safe harbor statement, we will talk about some things that are not yet generally available, and we're not making any promises about whether they ever will be. And especially not about when. So the vision of MySQL Cluster is to become the default database for any application that's real time, and by real time here we mean your response time is bounded. You need to be able to predict that with great confidence that it will be within a certain range. Transactional, at scale, and where downtime is simply not an option, right? MySQL Cluster is a product that's been evolving towards that over many years, and I wouldn't have said a year ago that we were there, but today we can go out and make this statement. So here, big slide full of logos. Who's using it? Some of the companies on here, the ones that have been here the longest, are either they operate telco networks or they sell equipment to people who operate telco networks. So the origin of MySQL Cluster is in this database that you embed in a situation where, and let's talk about network operators and some of the requirements they have. There is no such thing as a planned maintenance interval, right? The phone system does not go down. A change of a schema is an online operation. A backup is an online operation. An upgrade is an online operation that we call a rolling upgrade. So you start with one node, you upgrade it. Your cluster enters a state where it has to understand that some nodes are running a different version of the software than other nodes. You keep going, you upgrade the next one. Eventually, you get to a point where the rolling upgrade is complete, and the whole cluster understands that it's running a new version and that new features are available. Right. The newer customers on this slide, some of them are online games. I've got Zynga and Blizzard here. So they've taken those requirements to online gaming where the reliability and the availability are still required, but the use case is a little more general. Back in the telco days, all queries were simple and all production code was written in C++. Going into the gaming world, there's not so much low-level C++ code. Either you use the APIs we're going to talk about, or you use SQL. And part of the ability to do that is based on the MySQL Cluster 7.2 release, came out earlier this year, and really made joins perform the way people expect them to, because where the SQL node, the MySQL server, used to have to fetch a lot of data from the data nodes and run a join there, moving the data to the query. Now we move the query to the data and we push a lot of that query, a lot of that join logic down to the data nodes. So the design goals of MySQL Cluster, then this sort of summarizes what I've been saying. To scale out both reads and writes, because it automatically shards out your data. It's got a sort of a multi-master kind of topology where any node can go down and the cluster stays up, and you can add nodes and get greater parallelism because you've added nodes to a cluster. Very high availability because any node can fail, any network link can fail. There should be no single point failure that brings the cluster down. And it can heal itself, and operations like upgrades and backups are online. The performance is real-time bounded. Now, the heritage of that is that we started as an in-memory database. And an in-memory database is a sort of a specialized concern, right? The evolution has been so that now you can have tables with data on disk, but all of your indexes still have to fit in memory. So it's a kind of a hybrid model here. Even though it's always been an in-memory database, it's always been a durable in-memory database. So actual transactions happen at the speed of memory, but there's always been a checkpoint process running in the background, writing that stuff to disk, right? And then we get to the really interesting thing about a shared nothing cluster, which is when a node comes up and rejoins the cluster, there's a node recovery protocol, which is where a lot of the magic is. So SQL and NoSQL, meaning we want it to perform really well as you expect from the MySQL server, even to the point of reporting type queries, data warehousing type queries. And yet, for operations, we wanted to give you high-performance APIs. So that starts with the C++ API we call the NDB API, which is high performance, but it's also very large and complex. And from there, we build APIs which we hope are also still high performance, but much easier to use. When you put all this together, so here's the basic architecture. Down here at the bottom, these are data nodes. These guys store the data. There's a management server here. The management server actually plays a surprisingly small role in the cluster. It has to be there for another node to connect. It has to be there to start a backup. That's primarily what it's for. And then all sorts of other nodes connect as API nodes. And by the way, there's no real security between this layer and this layer other than the configuration file that tells the management node whether a node is allowed to join the cluster. So normally all of this stuff is on a private network, is on a private dedicated gigabit Ethernet. And the real clients, whether they're mobile devices out in the world or web servers or front-end web servers, connect to that cluster, connect to the API nodes over a different network that has a different security policy. So we're going to talk about Java API, and Craig will mostly do that, and then I will talk about Memcache API, which is usable for any language that has a Memcache client. So Java has one called SpyMemcached that serializes Java objects, and we can use that. Ruby has a similar one, and then Perl, PHP, Python all have Memcache clients that are used heavily. And then finally, we'll talk about the newest product, which is just had its first alpha release, and the APIs are not quite stable. We're still actively doing a lot of work on it, and that's our JavaScript connector for Node.js. So Memcached, which I will get into more detail here later. Memcached is basically a key value store, and with a little bit more to it than that. And we've got a Memcached server that on the front side speaks this Memcache protocol, and on the back side can stores everything in MySQL Cluster, or maybe even stores it and also caches it locally. And then here's where I'll turn it over to Craig, and we'll start getting into more detail about all of these. ClusterJ is our set of APIs or our ecosystem for the NoSQL access to MySQL Cluster from Java. And here, I'll give it back to Craig to tell you more.
Okay, thank you, JD. So just two more questions before I dive into the nitty-gritty details. How many of you consider yourself to be competent in JavaScript? Okay. And I guess I'll leave the other question for later. No, actually, the question is, how many of you are expecting to see some code examples today? Today. Yeah, in the next 10 minutes. Okay, we'll get right into it then. So the official name of ClusterJ is the MySQL Cluster Connector for Java, ClusterJ. And it's kind of a mouthful, so we're just going to talk about ClusterJ today. And what ClusterJ is, if you Google ClusterJ, you find that we've pushed out the cluster I and the cluster K and the ClusterJ back into the background. So you can still Google cluster K and you can get a bunch of variant analysis, but ClusterJ sort of pushed all that stuff aside. what we've done with ClusterJ is basically written a very thin Java wrapper around the C++ APIs, and done it in a way that is, for Java developers, can be a lot easier to grok than the C++ native API style of doing things. So hopefully at the end of this you'll get some idea of where we got some of these ideas. I have to tell you that we looked at other domain object model persistence APIs like Hibernate and JDO and Java Persistence, and we frankly stole some ideas from those folks. Actually, they borrowed some ideas from JDO and other things that came before, but we're not keeping score anymore. So we've achieved a lot higher performance than JDBC, mostly because if you look at this diagram, your applications can go through JDBC, ending up through MySQL, and then MySQL actually, the server actually has a C++ component that is part of the network. So we bypass that and end up going directly from your application through ClusterJ with the JNI in the node itself to talk to the cluster. So we bypass the SQL entirely. And so what we've hoped to achieve with this is higher productivity, higher rate of adoption, and actually less issues dealing with C++. You know, if you forget to undangle a pointer, you'll end up crashing your entire VM, and that's not generally a good thing. So we've made this thing idiot-proof or bulletproof. I'm not sure, they may be the same thing actually. So ClusterJ, here's some just examples of what you can do as a NoSQL store. Your mileage may vary, your application certainly will be possibly richer than these, but we can use this as a key value store with arbitrary text storage. Strings are mapped to clobs. You can do arbitrary data storage with byte arrays, so you can do binary operations. You can use it as a document store. You can store JSON objects in it, and you can also index the JSON objects any way you like and get some relational performance with JSON documents. One popular approach we thought would be a session store for your Java EE or your web session storage. Key is the session ID, value is the serialized session state. So it's a very quick way of dumping state in so that you can achieve load balancing. Any node can retrieve or can receive a message from that session and then immediately get and restore the session state from that object. And we've experimented some with a backend for a REST plugin. So your normal operations, get and put operations can very quickly be implemented using this API. So if you're not familiar with domain object model mapping, it's one of the concepts that's used a lot in Java and other APIs. We basically take tables in your relational database and map them into classes or persistent interfaces. And I'll get into what a persistent interface is a little bit later. Columns map to properties in your object. The column names default to the property name in your objects. And rows map to persistent instances. So it's a very straightforward mapping. What we don't do here is inheritance. If you need inheritance, we're not quite there yet. And we don't do joins. So joins are pretty much on your own at this level of the API. We're of course looking at implementing joins across the entire range of APIs in a way that takes advantage natively of the very high performance that we've just come out with the Cluster 7.2, where joins are actually implemented at the data layer instead of at the SQL layer. So I'll leave it at that. You do annotations. They're either Java annotations or, well, in case of JavaScript, the annotations are actually a class as opposed to in Java where they're native. And you get to choose which you would like to do. Either you write a user interface and then ClusterJ implements a class that implements that interface, or you write a persistent class and you subclass from a persistent capable base class. So here's an example of a generated class. approach, you define an interface called tweet. You annotate it with a table name, and the table name is tweet. And then you do normal Java get and set methods to implement the attributes that correspond to the table. So there's an ID column, an author column, a timestamp column, and a tweet column in the database. This is the approach if you want to write your own class, and this allows you to implement domain-specific behavior, whereas the interface, you don't get domain-specific behavior, you just get your basic gets and sets on the object. So this is, if you want to implement your own behavior, this is the way you do it. So that's just this thing is driving me nuts. The table method is part of your class, and the table method implements the return value is the table name that you want to map this to. So it's very trivial, very straightforward to get going. Each of the attributes is mapped to a value get or set. This is pretty straightforward stuff. Get 0, you say, well, how do I know what the column 0 is? And it's all in the metadata. So the metadata is available to you as well at runtime. Okay, I'm going to go quickly through this. Most of the domain types that you want to use in Java have been mapped to types that are native to the data store. So Boolean, byte, short, integer, long, float, double, big decimal, big integer. We map those to the appropriate data types intrinsic to the store. So again, this is not SQL types. These are native types in MySQL Cluster. We have all 4 date time, timestamp, time, and date. And you can map Java util date to those things. Java SQL date normally maps to a date. Java SQL time to a time. And timestamp, you get to choose between a date time and a timestamp. They have somewhat different characteristics. One of them is a Unix time seconds since the epoch, whenever the epoch was back, before some of us were born, I think. And then we have variable size column mapping. So you can map strings into chars, varchars, or text, which is basically a blob type. And byte arrays map to binary, var binary, or again, blob types. So ClusterJ interfaces look very similar to some other patterns that you may have seen in Java persistence. There's a session factory, which is basically your connection to the cluster. And you can have a database identified. The session factory, as you might guess, is the factory object for producing session objects. The session is your connection, your personal, private, non-shared connection to the database. So most of the heavy lifting in this API is done with a session object. So you've got to grab a session object, do some work, and then put it back. There's a transaction object that allows you to have fully fledged transactional behavior where you have multiple operations in a single transaction. But as an ease of use thing, if you just don't do anything with transactions at all, you get the auto commit behavior that you're probably familiar with from the JDBC interface. And then queries is the way you get lots of data from the database. There's also a very straightforward way of getting an object by key, which goes at blinding speed. But query is a way you can issue a query. You can navigate through a number of tables, a number of indexes on the tables, and you can pull back a range of objects. So here's the view of ClusterJ, and it turns out that's also the user view of the Node.JS adapter as well. So it turned out to be a very useful paradigm. You have configuration properties here, and the configuration properties are just what you'd expect as the Java properties object. The session factory is configured using that, and once you have a session factory, this is especially cool for a web server or an application server, because you typically have a single session factory, and then you can very quickly manufacture sessions from that. So it's a separate modeling paradigm that you can use, especially appropriate for a server environment. Here's the way you configure this thing. You properties, new properties object. You initialize the properties object with a couple of things. In fact, these are the only required properties. There are lots of other properties that you can set in there, but these are the ones that you want. One is the connect string, which tells you your host and port number to connect to, and the second is the database that you want to connect to. So those things are encapsulated in here. As a side note, you can have this, we will actually share a session factory among multiple databases, and that's all done behind the scenes. But it's useful to have a default database when you're connecting to a cluster. So the default database is part of this encapsulation into the session factory. And then here's the money shot. The get session factory is a method on ClusterJ helper that returns a session factory given the properties that you've initialized for it. So again, we don't assume that we're going to read a file. If you want to read a file with properties in it, you can do that. We didn't figure that that was something that, as an API designer, we needed to do for you. So you can go and read your own properties from any object that you want to, and just deliver that properties object when you construct your session factory. So now that you have a session factory, from that factory you can get a session to do your work, and the session is a factory for persistent instances. So it's a factory of factory kind of notion here. The session also manages the life cycle of the objects. So you create an object, you can persist it in the database, you can delete it from the database, and we try to maintain the connection between an object in memory and the row in the database that corresponds to the primary key in that object. So persist is the API you use, and persist says, I guarantee that there's no object like that with that same key in the data store. And if there is an object with the same key, you get an exception. Remove, similarly, the record, the row must already exist in the database. You can do an update. You don't need to read the object first. So that's an interesting thing. It's a little different from some of the other APIs you may be familiar with. You can just create an object with the primary key and some fields, and you can say, update the object in the database. You don't need to read it beforehand. Of course, you can. If you want to read it beforehand, you can, but you don't have to. It'll do a blind update for you. Your choice as an application developer. Similarly, the save API, this is real cool if you say, I've got all the data that I need for an object, and if the object already exists in the database, I want you to write it, and if it doesn't exist, I want you to create the record in the database. So it's a very useful paradigm for many applications that really don't care, like the honey badger. They don't care if the object exists. They're going to overwrite whatever it is in the data store, and sometimes that's useful. The other thing that the session does is a find by ID, and that's a very fast operation. If you have the primary key of the object, you give it to the session, and it gives you back the values from the database in the domain object. And of course, there's a query factory. The query factory is very much like Hibernate or JPA query, query anyway. So that you get a query factory from the session, and that gives you query objects that are specific to your session. So you're not interfering with other users of the database. Okay, here's some code that implements an insert. So you start by getting a session, and this is a very simple operation. Get a session, create tweet, and this is the domain object. You do a new instance. So session is a factory for new instances, and it's an instance of the tweet.class. And then you do set ID, set author, set tweet, set timestamp, and these things. So you really only have to provide the author and the message, and you can create this with a random UUID, and you can decide for yourself whether UUID.random is a good key for you. But in case it is, we can pretty trivially create those things. So you can also implement other styles of creating primary keys. That's just a real example. So the last thing you do is session.persist. And of course, the session.persist, since you haven't mentioned transactions at all, that's going to be an auto commit operation. So at the beginning of this, there was no such object. At the end of this, persist, that is the very next thing, you have persisted the object in the database, and you're free to do whatever you want to with it. So here's a case of find, where you want to find an instance of the object in the database. You provide a string, which is the ID, corresponds to the UUID.toString, and the find will give you the instance that corresponds to that ID. And this is one of the things that we do is we say if there's no object in the database, we just return null. We don't throw an exception, we just give you back a null. And if you get a null pointer exception, that's your problem. Sorry. It's easier to test for null than to catch an exception and do all the stuff that is exception. Yes, question?
Yeah, on the previous slide, what about when you say when you want an auto-generated ID?
The question is, if you want an auto-generated ID, that is, you want to put this set ID, and the answer is we don't support the data store providing that at this point. So that's a good forum question for a future release, and no commitment, but that's an interesting thing to do. Okay, so transactions. Does anybody here want me to go through this whole description of transaction? Okay, everybody knows what a transaction is. You can begin, commit, rollback. You can set rollback only, get rollback only. If you the set rollback only is really for the cases where you're working in one part of your application and you realize that there's some tragic failure, that it's not really an exception, it's just a condition that you just don't want this transaction to commit. You can say set rollback only, and if you try to commit that transaction, you'll get an exception there. So it's a way of distancing the application knows that there's some problem from the part of the application that is actually going to do the commit for you. And here's an example of creating a number of objects in the database. So at the end of this, we're going to create a tweet from Amos, Barb, Chuck, and Dave, and the whole thing is going to either commit or roll back as a group. Pretty straightforward. Okay, so that's a really tearing through the API, and we now have another API for your consideration. Oh, one question? Nope, just a yawn. Okay, I understand.
All right. So all of this stuff can be used together, right? We just saw, creating records through Java, through ClusterJ. And those are going to be visible through SQL, right? And they can cooperate with some other code in some other language, maybe using this API through Memcache. And really, the reason we chose Memcache, a big part of that is that we had a good NoSQL API for Java, and we wanted to move on to something that's cross-language, something that will be accessible from a wide variety of languages. And so Memcache fits the bill. And we look at it from two different perspectives, kind of. From the MySQL cluster perspective down here at the bottom, we think of it as that high-performance, easy-to-use API from a bunch of languages, and also can supply an extra layer of caching, which might be handy sometimes. From the point of view of Memcache and Memcached and people who already use it and are familiar with it, it is traditionally just an in-memory distributed hash table. When you connect MySQL cluster to it, it becomes a persistent data store, right? It traditionally exists kind of alongside the persistent data store, and now here we take the Memcache and the database and combine them into one. So this is the basic idea. This goes back about 10 years ago. It was developed at a social networking site called LiveJournal. Still the most popular social networking site in Russia, I think. So there's an application. It's written maybe in Perl, running inside an Apache web server, uses a Memcache client. We've got a key, and we want to know what data we've stored with that key. So we hash the key, and we use the hash value to pick a Memcache server from our pool. And then, okay, so we pick a server. We go to that server with a key lookup, and that server hashes the key again, looks in its big in-memory hash table, and gives back the value, right? So this is something that, maybe there's not enough memory in this server for the whole data set. So you just add a server, and then because you hash them over here to pick the server, you can scale this to whatever degree. And it's basically key and value. There's a little bit more to it than that, but there's not so much more that I can't exhaustively describe the whole thing in the next 3 slides. So the protocol has these elements to it. There's the key. The key's up to 250 characters. By the way, there are really two versions of this protocol that run in parallel. There's a text protocol and a binary protocol. So in the binary protocol, the key might be 250 characters of a binary string. There's an expire time, which is a number in seconds up to 30 days. There's a 32-bit value called the flags, which is completely opaque to the Memcache server. The application supplies flags, and the application gets flags back, right? The server does nothing with them. There's a 64-bit value called the CAS ID. CAS here means compare and set. This is used as a version number check on the stored record, and it can be used to implement a kind of optimistic concurrency control, and we'll see that. And then finally there's the value. And the traditional limit on the value is that it can be up to 1 meg. But actually that's implementation dependent. In our version, in our NDB server, if you keep the value under 14K, you can store it in 1 row of the database. And you have a performance advantage in doing that. You can actually go over the 1 meg if you store it as a blob, but you have to pay the penalty of the fact that it's divided up into actually many rows of a table. So that's the complete set of elements of the protocol, and then we've got about 12 commands that go along with those. So get a key, the client supplies a key and wants to get back the value stored. Set a key and a value, the client supplies the key and the value, and the server stores it. And then there are some varieties of set. So add is a set that's a strict insert. It only stores the value if it does not previously have one, right? Replace is a strict update. So it only stores this value if it does already have one. And then here comes the version number check and the concurrency control. For CAS, the client supplies, here's the key, here's the value I want to store, here is my CAS ID, my version number. And the update will only succeed if the version number on the server matches the one the client supplies. If there's a mismatch, the server sends back an error, and the client processes that error to go start again, get itself current with the database, and somehow recover from the situation that it had a stale value.
Is there no remote?
Go on. Yes?
No, I see it right there.
Okay. Then the rest of it, you can append and prepend. You take a value, you take the text of a value and you add it before the current value or after the current value. Increment and decrement, you treat the value just as an integer counter and you add to it or you subtract from it. The decrement does not flow below 0. It has error trapping at 0. Delete the client sends a key and wants the server to delete the value stored with that key. Flush all is an operation that's has a lot of use in a cache server. You might clear the cache. In a database server, it's a little scary. It would translate to delete star from table. So if you want to enable it, we let you enable it. But we give you control over whether that's honored or not. And then finally, the Memcache server can supply a lot of different operational statistics, and there's a stats command that lets you get them. So when you put this all together, you've got an application in a wide variety of languages. It's got a Memcache client for that language. Connects to this. Here's our NDB Memcache server. It consists of the Memcache layer and the NDB engine layer. And then you go here. This part is the private part inside the cluster, and you go to cluster data nodes and actually run the operations. So finally, compared to traditional Memcache, there's obviously a performance penalty in this architecture, because where originally you just had one network hop here, now we've got two network hops here. And we want to measure the performance of the whole thing and measure the impact of that. I think this slide shows pretty succinctly that it's no worse than it should be. So here's a ping time between the test client and the test server. If you about double the ping time, you get to standard Memcached, what we now call the Memcached default engine. And here my green diamond is the read time and my blue one is the write time. And you sort of double that again, both for the one node cluster and a two node cluster connected as a backend. So the top of this graph is 1 millisecond, right? Where still everything is below a 1 millisecond. And in our worst case, which is the write performance for a two-node cluster, the 95th percentile performance here is still at 600 microseconds, so well within the millisecond. And then our average is just about 400. So your average time is below half a millisecond here. And this is, my client here is called Memcache test here, and I'm, the parameters control the value size and other things that I forget. So SQL access, Java access, Memcache access, those are all production available in MySQL Cluster 7.2. I'll spend a few more minutes talking about what we call the MySQL Cluster connector for Node.js. And this is brand new code that we're just starting to make available. Not stable for production yet. Almost stable for development, but maybe not even that. So Node.js is a web application platform. And you might say in some ways it is the polar opposite of the Java EE app server. Because a Java app server is multi-threaded, probably runs really well on CMT machines with lots of cores, lots of processors. I think that generation of Sun hardware was about running a Java app server at lower cost, lower heat, lower power consumption in the data center. Node.js is single-threaded. It is event-driven. It never allows your main application to block for I/O. It is supposed to handle a really high number of connections with a single core and a low amount of memory. Partly it does that by never giving you a stack. Whenever you do something that's going to wait for the disk or wait for the network, your application gives up control, gives up its context, and that context comes back a little later in the form of a callback when your operation completes. So this is going to look a lot like the Java code. Here's a JavaScript constructor for the tweak class. It again generates a UUID, generates a timestamp, takes a user and a message. When the Node.js starts up, there's a little bit of startup code where you require the adapter, MySQL.js. You also require the built-in web server module, the HTTP. You take my constructor that I just showed you, and here's the annotations. We're going to say NoSQL, which is what we got when we required the module, map the class, give it the constructor and the name of the table. And then we're going to get a session factory, just like the session factory in ClusterJ in concept. Connecting an NDB here is the name of an implementation that we're using for the background connection with all of its default properties. In this case, it's NDB, but it could be MySQL. So we've got the native MySQL cluster connector, the NDB connector here. But you can also do this with NODB or anything that any kind of server out there that speaks the MySQL protocol can be a backend. Starting up the HTTP server, so we're going to create a function that's going to run when an HTTP request comes in. It takes the request and the response. And what that function is going to do is call our session factory and get a session, right? On session, here's another callback with the HTTP request. And then create a web server. And what the web server is doing is when a request comes in, this function is going to run. You see this sort of bottom-up, backwards nature of event-driven JavaScript here. Here's on session. So this is the function that's running from the on-tweet request, right? On session. Here we've got an error condition, a new session, and a request. And basically, we're going to call the constructor, the tweet constructor, using the user and the message that came in from the web server. That gives us an object, and then we use the session and we persist the object. And do some response acknowledgement back to the web client. And that's really it. The rest of this might be waiting for this to execute and recording the error condition or the success and letting the client know. That's what this stuff is. So it's a very straightforward mapping from the development paradigm for Java that is supposed to be easy to use, supposed to supply this low overhead bridge between the realm of application logic and the realm of the database. But for the event-driven JavaScript server in Node.js, which is a really different operations paradigm.
Question?
Yes. Does the persist call block? So let me talk about this here, actually, on this slide. The persist call does not block. It takes a callback. So this was a big decision about how to design this, is that if every call was synchronous, if there were a lot of synchronous calls that blocked in our single execution context, we would get low performance, right? So we do have a few calls that are synchronous. They're part of the server startup. They make your logic a little straightforward. Since you can't do anything until you've connected to the server anyway, we let you connect to it synchronously. If everything was async, the code would be a little more complex than it has to be, because each individual operation would be nested with its own callback. So what we think the balance is that you can define an operation as an immediate call, and then you execute them. When you execute them, you supply a callback and go to I/O. So here in the case of persist, if you were inside a transaction, so if you had used your session to start a transaction and you were going to do multiple operations, persist would be immediate. Because you're in auto commit mode and persist is your one operation in the transaction, we're actually going to give it a callback here, and persist is async. So individual operations are immediate. Calls that execute are async calls that have callbacks, and it so happens in the simple one operation auto commit scenario, the call that defines it also happens to be the one that executes it, and so it's async. That's the whole story. I think we have some time for more questions. MySQL Cluster, the best of both worlds, means joins reporting queries through SQL and operations through all these lovely APIs that we've talked about. So thanks very much.
But wait,
Okay.
there's more.
Oh, yes.
If you're interested in actually getting your hands on some of these tools, we're having a hands-on lab tomorrow in the Hilton Franciscan room at 2 o'clock in the afternoon. It's a 2-hour lab. You'll get a chance to actually spin up a cluster yourself. We'll have access to all 3 of these APIs for your viewing pleasure.
And I think we have a question in the back.
Yes.
Memcache support some kind of replication between a remote?
Does the Memcache support replication? So yes. MySQL Cluster, generally one cluster runs at one data center. You can have a cluster in one location and a cluster in another location and replicate between them, right? And yeah, and that is a 2-directional replication. It's got a little bit more in it than standard MySQL replication because it's got 2 masters and we do some conflict detection. So the Memcache client is making data changes on the data nodes, and really there's a MySQL server in each cluster that has the role of managing the replication channel. So it sees those changes and it sends them over the network to the other side. So yes, it's sort of a big complex situation, but it does work. Yes, with 2 directions, and so it's synchronous inside your one cluster in your one data center, and then it's async to the other location. Here, yes.
2 quick things. What's the overhead on the client side for pulling in the Memcache client? And also, can you talk a little bit about the security of all this SQL stuff within JavaScript?
So the security within JavaScript right now, again, there's no right now the way you would have to build it is that your JavaScript, your Node.JS app server is inside the private network, and then there's a front-end web server that is outside that network that is being a front-end proxy to it. So the Memcache client overhead, I'm not sure I understand what you want to know. It's Memcache. It's a really simple protocol. The clients are usually only a few hundred lines of code. It's been heavily tweaked by people like Facebook, so that there's a TCP version, there's a UDP version, there's text and binary. I think when you get down to using the UDP protocol over binary, it's really pretty amazing in terms of low latency.
Why haven't you decided to use an existing API for ClusterJ, for example, GTO or UPA? with some restrictions. But why did you introduce the whole new API?
Okay, so the question is, why did we introduce yet another persistence API?
Yeah.
Yes, and the answer is we actually do support JPA with a special version of a plugin to an existing JPA server. So
I saw it's a JPA through JDBC and through MySQL server.
that's true.
But I didn't see JPA through ClusterJ.
Right. One of the slides there had Cluster JPA, which is actually built using this, but also if you have a complex query, the complex query goes through JDBC. The simple, straightforward query goes directly through ClusterJ. So we did make an effort to do that. You probably can appreciate that that JPA is a very complex, very large API and has a whole set of issues dealing with. You can't advertise it as compliant unless you pass the compliance test suite. It's a relatively small project within MySQL. We didn't have all the resources to actually sustain that kind of effort. So we actually implemented a plugin to OpenJPA. And the plugin for simple operations goes directly to the database. For complex operations, delegates back to the JDBC path. Yes?
In a column, you can pass a foreign key, right? It's possible to pass.
As far as the question is, can you pass foreign keys or can you use foreign keys? The answer is foreign keys are implemented in the database, and therefore we don't care.
Basically, in a transaction, I can create an object and then put his ID into another object.
Yes, okay, so the question is really how do you navigate from one table to another using foreign keys? And the answer is you define each of the tables independently, mapped independently. You retrieve one object, you take the value and use that as a lookup into the other table. And that works at the speed of MySQL, actually, because that's exactly what MySQL is doing in the cluster environment. It's looking up the two things and making the join basically in the server itself.
So if you use JPA, JPA is doing that for you, when you can map other objects?
Yeah, if you're using JPA through JDBC, it's going to the MySQL server, and there are some optimizations, some queries with joins can actually optimize. But we're also looking at extending the ClusterJ API to include doing the joins inside ClusterJ, and therefore pushing it inside. But that's one of those safe harbor things. We can't give you a date. It's just a feature that we're very actively looking at.
And then there's another part of that answer that actual foreign key constraints are not enforced in the current release of MySQL Cluster 7.2, but they will be in the next release, 7.3.
Yes?
You're using NoSQL databases to massively scale out. How many nodes can you support with the MySQL solution? Maybe you would need 100 nodes.
Yeah. So 48. So we have a limit today of 48 data nodes.
Data nodes.
Yes.
But how many application nodes?
Some other 200 application nodes. So it's not something where it's not like the domain name system, right? Where you don't even count the servers. It's a small cluster.
I think we're sorry.
Do you have any plans to change it?
I think by design it will always be finite, but we do have plans to make it larger.
Okay,
Yeah.
I will not ask that.
Yeah. Please don't. Yes.
Okay.
Thank you.
Thank you.